Today in Math Extension 1, Ethan generates equations using projectile tracking software, Gordon researches a Chinese crane, and they both see if a hypervelocity grenade can be shot at Dwayne Johnson. This is Projectile Dysfunction, investigating if Dwayne Johnson makes that skyscraper jump.
To determine this driving question, we'll need Johnson's initial velocity, which can be found by his horizontal and vertical vectors through analyzing behind-the-scenes footage of his jump. Landmarks like the distance between headlights inform us the distance Johnson ran, generating his horizontal velocity at 9.63 meters per second. Due to the parallax error from the camera angle where we analyze Johnson's jump, however, calculations of his velocity may decrease in accuracy. When Johnson jumps, his feet become angled as he increases in altitude, allowing us to create a right triangle involving his vertical displacement. If we time this via Adobe Premiere Pro, Johnson's vertical velocity is around 9.14 meters per second. With the vertical and horizontal velocity vectors, we can calculate Johnson's initial velocity, providing us with an initial velocity of 13.2816 meters per second. As for the angle of projection, this is done in 5 methods. First is applying inverse tan on the aforementioned horizontal and vertical vectors. Second is via raw video analysis, where Microsoft's layout tool measures Johnson's projected angle. Third is applying the inverse tangent function for the vertical displacement of Johnson's hand on his horizontal displacement relative to his jumping point. Fourth, we used the projectile tracker and extrapolated Johnson's initial jump. From this, the initial velocity vector can be disassembled into vertical and horizontal components using Excel, where the projected angle can be calculated through the inverse tangent function. Fifth, we expanded on the tracker software's data, forming parametric equations which allowed us to form a Cartesian parabolic curve of best fit that represents a Johnson's jump. We then used the gradient function on this curve at x equals 0 where Johnson jumps and applied the inverse tangent function to find the projected angle. With the angles found, an average will be calculated at 49.0695 degrees. This is because the average is statistically closer to the true value than individual data points.
Moreover, we can use the obtained curve of best fit to extrapolate Johnson's jump and determine if he makes the jump. With the established setup of the coordinate axes, we have made the point where he should land lie on y equals 0. Thus, at the height of the point where he should land, he is 27.0897 meters from the crane. Through the tracker software, the horizontal distance from the crane to the window is measured as 30.50 meters. Thus, with our calculations, he is projected to miss the window by 3.4103 meters.
To reinforce the previous conclusion, the clips show a tall crane winch hooked to the pearl. We've researched the crane in the movie to most resemble a Chinese tower crane whose winch length is 32 meters. Another right triangle can be created from this to find the distance between the crane and the pearl. With this, we can generate a diagram and integrate the following equations of motions as shown. We simply let y equal the maximum altitude Johnson can drop to and x equal the maximum range that Johnson must travel or else he dies. If we crunch these numbers, it's shown that Johnson does not make the jump as confirmed by a Desmos simulation. Note that the use of the tracker software, however, is limited by the poor video quality when zoomed in and also doesn't fully account for the resulting dimensional distortions.
So we've projected that he's most likely going to fall to his death. Now let's make this a bit more quick for his sake. Consider this scenario. A grenadier is tasked to take down Johnson. This alternative situation delves into a collision scenario between Johnson and another projectile, a grenade, as shown on the screen. What angle should the grenadier aim so that his grenade can collide with and annihilate Johnson? To find this angle, let's break down Johnson's jump and the motion of the grenade. Using quick integration and maths, we find that horizontal and vertical components of Johnson's jump are as follows. The same applies for the grenade's equations of motion, though the horizontal velocity of the grenade will be negative as it's moving in the opposite direction. Now we can equate the equations for x and y in the motions of Johnson's jump and the grenade and rearrange them to eliminate the t or time parameter. Eliminate the parameter by equating the equations for t, and we reach an interesting equation with 2 different trigonometric ratios involving sine alpha and cos alpha. This is rather hard, which is a bad sign, but no need to worry because we can apply the auxiliary angle. We're now getting good signs now, so let's use the sign subtraction expansion. Equate the respective terms of sine alpha and cos alpha. Because they are trigonometric ratios, we can illustrate these equations in the form of a right-angled triangle and solve for r and the auxiliary angle q. Thus, we can rewrite the equation as: substitute this equation in and easily solve for that destructive angle. With the above calculations, the angle is shown to be 87 degrees and 11 minutes. Overall, we've calculated that Johnson's jump is unfeasible, and have developed an alternative scenario from our mathematical models which accelerates his fate. This has been Projectile Dysfunction, and we discourage jumping off cranes, or you might be projected to dysfunction yourself.